Hi. Today we will be going over the flexible diaphragm homework solution. Now I've chosen the hardest one out of all. These two are very basic, and then finally this is something that's a little more challenging and something that is at the level of a midterm. This is what the expectation is for a midterm. So I wanted to go over this one, which we would go from case by case to solve everything. Okay, so we'll take it nice and slow. And we'll focus on seismic loading. Now, the total base shear applied to this building is 8,000 pounds in the north and south direction. Note this is a flexible diaphragm. So what that means is that the load is either going this way or this way, right? But in this case, we're really just analyzing going in one direction, okay, this way. And alternately, another question could be like, well, what if it's going this way? Now, if the question actually asks for that right now, the thing is there's no line of resistance being identified, so you actually would not be able to solve for this problem, period. So what you see in dark red is a shear wall. So these are shear wall, and this is a shear wall. This is a drag element, right? It drags the force into that shear wall, okay? All right, so we'll go ahead and get started with, first is distribution. So A, solve for distributed load proportional to the area of the building and draw it. Okay, great. So let's see maybe if we could do it like this. Screenshot it. And we'll say we're going to add, oh no. We're going to say that we're going to add a sheet right after this. And we will do that. Go ahead and cut it so it's nice and clean. Done. Right. Now solve for distributed load proportional to the area of the building. Great. So first, what we need to do is actually find the area of the building, and then from there, make it proportional. So this is just area distribution, right? So what is the total area? Let's start that AT, total area, is equal to, let's see, I think what's not noted here is that that's 55 feet. So I don't know how anybody solved for this since that wasn't listed. And so that means that this is 65 feet. Okay. All right, so we'll do 55 feet times 100 feet plus 65 feet times, it's going to be 45 minus 100, which then gives you 55 feet. Right, so let's say that this is A1, this is A2, that's your A1, that's your A2. And when we do that, it comes out to be 9,075 feet squared. Great. All right. So we want to know what the proportional area, a load to the specific area is. So then let's just do F1. F1 is equal to 8,000. And then what we're saying is that we should actually write what A1 is in terms of area. So A1 is equal to 55,500 square feet, and A2 is equal to 3,500 75 feet. So you'll take 8,000, which is total base shear in pounds, and you'll proportion it to the area, which is 5,500, 9,075, right? Which then is equal to 4,848 pounds. Okay. And then we'll say that the distributed, because we would distribute it across it, so we'll say that it's Q1 is then equal to 48 divided by the width of that, which is 55 feet. And you'll get 88 pounds per linear foot. F2 is equal to 8,000 pounds times A2, which is 3,575, divided by 9,075, which then equals to 3,152 pounds. And we get that Q2 is equal to 3,152 divided by the width, which is 65 feet, which is equal to 48.5 pounds per linear foot. Okay? So what that really means is that, let's do this. Actually, let's do this here. Crop. Cut it, so it's just that right there. Okay. We're saying is that we got 488. This, we'll make this larger. £88 pounds per linear foot. This is equal to 48.5 pounds per linear foot. That's essentially what we did. We proportioned the distribution by area, right? Very basic area calculation. Okay. So we move on to the next question. Well, what's the next question? Solve for the chord force. Okay, so if we cut that, we're going to solve for the chord. Max chord force. Well, it's pretty easy, right? So we'll say that this is 1 again, 2. Now the chord, remember, if that was bending like a beam, it would be like this, right? So what is the maximum moment? Moment is maximum at center. And then we take what we call a TC couple, right, for that distance, and we find out what the equal and opposite with the set distance load, right, essentially would equate to that moment. So what does that mean? Let's go ahead and look at 1. So if we draw it out like a simple beam diagram, do this, right, and we're saying that that's 88 pounds per linear foot. We're saying that this was a width of 55 feet. And now let's do the other one, right? Remember, the whole point of a flexible diaphragm is that you can break, span up. It's not that you can, it's more like you should. So we got 48.5 pounds per linear foot. All right, so what we're gonna do is find the moment and then take what we call ATC couple. Okay, let's do this in an organized fashion. I think we said that this was 65 feet. Yep. Okay, there we go. So, moment, WL squared over 8 is equal to, here WL squared over 8 is equal to 88 times 55 squared over 8. Right here is 48.5 times 65 squared over 8. And we find that the moment is equal to 33,275 pound foot. And this is equal to 25,614 pound foot. And TC, or chord, is equal to M over D, which is the depth, right? Which right here would be 100. And for this one would be 55. Okay. So M over D, and this is M over D. Let's go M1, M2, D1, D2, which is then equal to 3,300,257 divided by 100. This is 25614 pound feet divided by 55. And that is equal to 332.8 pounds. And this one is equal to 465.7 pounds. So the max chord force is therefore this. Okay. Solve for max chord force, and that's it. So we're done with B. Solve for max drag along B. All right. Previously, this was I think we're saying 88 here, and we're saying 48.5 here. All right, so this is going to help us down the line. So let's just solve for reactions at A, B, and C, okay? And we're saying this is... Okay, so A, reaction at A is equal to 88 pounds per linear foot times 55, right, which is the total length, yep, divided by 2. Reaction at B is equal to 88 times 55 divided by 2 plus, we got 48.5 times 65, which is in dimensions, divided by 2, right? Because this B line right here has half the tributary this, half the tributary. That reaction and that reaction goes into B. Okay, and then reaction C is going to be just 48.5 times 65 feet over 2. I think if we do this, all of a sudden a lot of other questions will flow pretty nicely. All right. So we find out that this is 2,420 pounds, 3,996 pounds, 1,576 pounds. Great. So when we do this, it says solve for the max drag load along B. Well, along B, let's clean that out. We're saying, so the question really is, what is the shear per linear foot, right? So shear per linear foot, let's put Q, right, is going to be 3,996 pounds divided by the entire length, which is 100, which is super sweet because that comes out to be 399.6 pounds. Oops. Pounds per linear foot. And the drag literally means how much of this length is it dragging. So therefore, drag is equal to 399.6 pounds per linear foot multiplied by that length times 55 feet. So therefore, the drag amount comes out to be 39? Shoot. 100. I'm sorry. It's 39. 39. Right. Yep. So that comes out to be 2,197 pounds of drag. Drag along B. Great. So we're done with C. Now, this is interesting. We can do D and E together. Okay, so first we'll keep this simple and we'll just kind of shrink this sucker right here. Get this resize. Put it over there. Okay. And we're gonna answer this question. Shear wall, which shear wall has the highest shear load? Okay. So what we do is we take our reaction and divide it by the entire length of the shear wall. Remember, entire length of the shear wall, not the entire length of that line. So in the case of B, it's a little different, right? So we take, oops, okay. So we're doing D. Highest shear per shear wall load. So let's do this. SWA, SWB, SWC. Okay. Reaction 2,420 pounds, 3,996 pounds, and 1,576 pounds divided by the length of the shear wall, which is in this case 100, in this case 45, and in this case 55. And so when we do that, oh, I'm sorry. So to do D, it's actually this. And so when you look at it, you're just saying what the term was load, right? So which one has the highest load? We would choose B because it has 3,996 pounds, right? So E is actually shear per linear foot, right? Shear per linear foot, shear per linear foot, shear per linear foot. So that comes out to be 24 pounds per linear foot, 88.8 pounds per linear foot, and this is 28.6 pounds per linear foot. Therefore, shear wall B at 88.8 pounds per linear foot has the highest shear per linear foot load on that shear wall. And that actually solves it. Now, one of the things that we could do is to check to see if we've calculated everything correctly. It's kind of late to do it at the very end. But say, for example, right here, we want to check. Now, remember this. We have this kind of shear wall like this, right? We're saying that the total load coming in, it doesn't matter which direction, whether north, south, or south, north, is 8,000 pounds. We're saying that the reaction here is 2,420 pounds. We're saying that the reaction here is 3,996 pounds. And we're saying that the reaction here is equal to 1,576 pounds. Well, guess what? These three loads need to equal that, right? Static equilibrium. And so if we were to add them up, it comes out to be, let's see, 3. So I'll do V prime is equal to 7,992 pounds. Okay, so we mess up on some fractional amount, right? Usually if it's less than like 2%, we say it's okay. And so that's well below 2%. So therefore, this is very similar to 8,000 pounds. So then we know that our distribution is on lock. All right, well, I hope you enjoyed the diaphragm series. Have a good evening.